This is a follow-up to my lesson 9, just the second part about horizontal projectile motion math. So we're going to look at some problems. We're going to know what equations to use during projectile motion. You're going to be able to solve projectile motion problems after this. So just a reminder from the previous lesson, we were looking at the x and y axis, the velocity in the x-axis. If you take a look at the ball down the bottom right here, it's in constant motion. And if you take a look at the y-axis, it's accelerating by gravity, the acceleration of 10 meters per second squared down. But if you combine those and you look at the middle ball, what's really happening is not either of those, but a combined motion. And so this little curved projectile path, once again called a parabola, is occurring. So just some information just to remind you about, if you know Vx anywhere, because it's going to stay the same the whole time the problem's going on, you're going to know it everywhere. The acceleration due to gravity is always going to be 10 meters per second squared down, but specifically because we're dealing with horizontal projectile motion problems that are going to be launched directly straight outwards, just like this, we're going to have initial velocity of 0 meters per second squared. Now, don't confuse it if I take your class into the next level and we go into angular problems. You're not going to be able to use some equations or versions of equations that we may use in this unit, because this might not be the case. But all these problems in this unit are horizontal projectile motion. They're all going to start with only a VIY of 0. Think about it, if a ball is rolling off of a counter right here, it's not going down yet until the problem starts. And then at that point in time, it's going to start curving and following that projectile path because of acceleration due to gravity and the constant motion in the x-axis going on at the same time. Now, we're going to look at when you can use, you might be asked for something else like VF after the beginning. You could solve for that. You can solve for the y component of velocity downwards. It's at the beginning that starts at 0, but it's gonna start to accelerate, and it's gonna gain this final component depending on where we're asked. And so you'll see an example problem where we do that. Just a reminder about the equations. Since the x-axis is in constant motion, there's only one equation we're going to use. And there's specialized versions of this equation that we're going to look at, which we're talking about in the x-axis. There's only one equation, and we might want to call this Vx equals x times t. I'll show you the specialized equations in a second. In the y-axis, and let me just show you a few things, we're going to call Ag instead, because it's going to be, in physics we have constants where the number doesn't change, and on Earth this g is going to be about 10 meters per second squared down. We just sometimes give a variable that's a common one like acceleration a special letter, meaning that it's going to be a certain number, at least on Earth. We'll see in a future unit that it might change on the moon or somewhere else. And then instead of saying x, we don't like to say x when it's in the y-axis. We're going to replace that x with y. So let me show you how we make these specialized. So every time we see an x, we're going to go ahead and replace it with y. It's really the same thing. So anytime we see an x, we replace it with y. And anytime we see an a, we're going to replace it with g, because that's going to be that the g is going to have that number every single time. Anytime you see a g, that's going in. So now they're specialized. Even beyond that, we might say, okay, in the y-axis, same equation. So don't get too overwhelmed by the facts here, but it's the same equation. They're just going to be specialized forms. Here's the x-axis equation right here, constant motion. This is just that equation rearranged. So you can choose where to start, v equals x over t, or x equals v times t. Really, it's just in the x-axis. And then this equation right here, I want to show you the next one first. So this equation, the y equals vit plus 1 fgt squared, if you're ever solving for how far down something's going to go, you can go straight to this one. In this unit, VIY is going to always be 0, so it pretty much cancels out this first part. And once again, horizontal projectile motion only. If we have angular projectile motion, this is going to change things. But since that first part's canceled out, this becomes y equals 1/2 gt squared. If I rearrange that formula, that's going to lead me over here. So what you really need to know right now is that if we're solving for y, then we're given time, we're going to do this. And you can even avoid doing this first part and even specialize that even further for horizontal projectile motion. But it's best just to keep it that way and just realize once you plug in 0 there, this first part is going to cancel out. Only horizontal projectile motion. I can't state that enough, because when we get to harder problems, this might change a little bit. And then if that's the case and this cancels out right here, if I rearrange it, I can solve for t doing this equation. So once again, only if VIY equals 0. If I have a height and I'm asked for a time, I'm going to go straight to here, and g is always going to be that 10 meters per second squared down. So really these are kind of the reverse depending on what I'm trying to get out of it. If I'm trying to get time or if I'm trying to get the height, I'll use one or the other of these. But in the y-axis, once again, if I ask you for the final velocity after so many seconds, and you know VIY 0, and you know it's after 2 seconds, you might want to go to one of these equations. You could still use these equations. You just have to remember, you don't have them specialized on your equation sheet. You have to realize they're the same equations. And the reason why this is important is a lot of physics classes, especially in college, will require you to memorize these equations. There's no reason to memorize them more than you need to. If you just know that these are the same equations and know how to use them, you can go from there. Okay, so some of the basics that you're going to hear in projectile motion, you're going to hear about a horizontal launch. That just means that VIY equals 0. And so it's not falling down until at the beginning of the problem. That's all that means. And you're going to be given some sort of Vx. It's going to stay the same throughout the whole motion. So anywhere else where you'd ask for Vx, it would be exactly the same number as whatever they gave you at the beginning if they gave that to you. You're going to hear height, and so height's just going to be y. If a building's so tall that ball's going to fall down off of that building, well, that's going to be your y. And then downrange is just how far from the base. So it's just talking about from here to here, how far from the base an object's going to land. A couple key terms you'll hear. And let's go ahead and try some problems. So there's two main types of problems. Some problems are going to start with enough information to start on the x-axis. Some problems are going to start with enough information to start on the y-axis. And now when I drew out the picture, it's very important to draw out a picture just so you can see what's going on and get your x and y givens right. Also, make sure that you go ahead and separate, make two givens lists. Anytime you can tell something is in projectile motion like this, you're going to follow the x and y axis as separate, but there'll be a key. One thing we know about this problem is this ball is going to pretty much fall at the same time it's going forward. And when it hits that ground, we are done with the problem. So once this hits the ground, we're not taking into account a balance or anything else. We're done with our thinking, our logic on the problem. We're only going to calculate through the fall. So there's one thing that's going to tie these two axes together, and that's time. So if we can get to time, we can go ahead and use that, and we can put that in the other axis. Let's go ahead and just walk through this problem. So you have initial horizontal velocity. It's going off the top of the cliff at 7.5 meters per second. We know it's going to fall, and this is going to be a y component. So once again, we're populating the x or y side depending on what given we read through, and we know it's 68.4 meters high. So the ball is going to fall 68.4 meters down in this problem. And then we're going to go ahead and throw in our other information. Once again, once you see the term horizontal, that means this. And then the ball is going to be in the air, so that's another given. So these are going to be givens. On horizontal motion, it will be always these two givens. You can just throw them straight in your givens list right off the bat. You don't even have to read the problem, but make sure as we get into some more detailed problems, has to be the case. They have to be horizontally going off of something or thrown horizontally forward. And then the question is asking you how far from the base. So the question is asking you right here, how far from the base from here to here, how far is that ball landing? And now, just like I said before, time is going to be the key. You're going to look at both these axes and you're going to determine, can I solve for time using this, or can I solve for time using this? And having two unknowns, you're never going to be able to solve for time using v equals x over t. You need to have at least one more known. So we're going to go ahead, and this is where that specialized equation from before, if you know the y and you know that VIY is 0, you can solve for time using this equation right here. So we're going to plug in our values. 2 times 6.8, 4 over 10 square root of that, and you're going to get 3.7 seconds. So at this point in time, once we got 3.7 seconds, we now know that it just fell in 3.7 seconds. It also is done going forward in 3.7 seconds. So this is where we can go ahead and take that 3.7 that we just solved for using this, and we can just plug it into the other axis. And now we can go to the x equals v times t. So we'll use the one that's already rearranged for us. And we'll plug in our values, 7.5 times 3.7, and we get 27.8 meters. You can be more exact if you want to say forward, but in general, it's gonna fall. This right here from there to there is going to be 27.8 meters after solving for this problem. Okay, so next problem, This is a different, this is the other set where we're going to start with enough information in the x-axis, and then we're going to have to pull that and throw that into the y-axis. So let's go ahead and start populating our x and y givens list. Make sure you have a separate x and y givens. We're going forward at, horizontally thrown forward at 44 meters per second, so that's going to be a Vx. It travels a horizontal distance to the plate before being caught. So it's telling you this, but it's really going to be the same as having that information right here as 18. So it's going to travel 18 meters forward. There goes the 18. And then other information, we're asked for how far does the baseball drop. So we're asked for y. And just once again, horizontal motion. It's going to start off with no VIY. Initial y is going to be 0 because it's not allowed to go down before it starts this problem. Once this problem starts, it's starting with initial velocity in the y-axis of 0. It's only going to keep that constant 44 meters per second. So we're going to plug in, we're going to have the ball in free fall, so that's going to be a y-axis given, and now we're trying to solve for time. And here you'll see you have two unknowns. You only have one unknown here, so we're going to start with the x-axis, and we're going to use this information to solve for the x-axis information. We're going to go ahead and you can rearrange it, or you can plug in the numbers, whichever way you do it. We're going to end up getting 18 x over the vx. So once again, if you could do it this way, you can say, okay, x18 equals 44 times time. Either way, you're going to divide both sides by 44. So you're going to get to that. Just make sure you're picking out the right variables. The velocity is not always going to be bigger. The horizontal displacement is not always going to be bigger. So just watch out. Just make sure you're picking out, have a givens list, pick out the right variables, and you're going to get 41.41 seconds. When we have 0.41 seconds, that is, we just solved for this, but now we can go ahead and populate the y-axis time with that too. And now we have enough information to go to our other version of the formula right here, and we can plug in a VIY0, cancels that out, so that becomes 0. So this becomes y equals 1/2 10 times 0.41 squared. Make sure you square the, don't forget the squared. And you're going to get, this ball is going to fall downwards 0.84 meters during this problem. So those are two main types of problems. I want you to work on this problem set and come back and check your answers after you're done. Maybe do a couple problems or one or two and just make sure you're doing it the right way. And after you get things down, just keep on working the whole problems and check your problem set. So I'm going to keep on working these, but I want you to pause the video if you're watching the video at home while you work these problems. Okay, so the first one, the stone's kicked 8 meters per second horizontally from a cliff that's 80 meters high. How far from the base of the cliff does the stone strike the ground? So when you think about this, okay, it's kicked from a cliff. The Vx equals 8.0 meters per second. You should draw quick pictures to help you visualize things. And then the y is going to be 80 meters down. It's going to fall down 80 meters. And now we can go ahead and start populating our givens list. So we have a Vx of 8 meters per second. We have a y of 80 meters down. It asks you for how far from the base will the stone strike the ground. So it's going to ask you for, you'll see it in a second, x equals question mark, but I didn't do it in that order. In the y-axis, it's horizontal motion, so at the beginning, so the VIY0, it's in free fall because it's in the air at that point in time, so the acceleration is 10 meters per second squared down. The question here that I underlined is asking you for x, and now you have time you have to solve for, and you'll notice you have enough information to start in the y-axis. So we go to our faithful equation. When this is the case, we can go ahead and solve for time, knowing nothing more than the distance it falls on Earth, where we know the gravity as well, being 10. Plug in your values, and you're going to get 4 seconds. Now the 4 seconds from here can be thrown onto the x-axis, and now we can go to this equation, solve for our x. We have a velocity of 8. If you're allowed to go forward at 8 meters per second, and you can do that for 4 seconds, you're going to get 32 feet forward. So that's what that's getting, and that's the answer to this problem. Let's keep on going. If you launch a ball moving horizontally at a speed of 1.12 meters per second, so I'll draw the quick picture here. So you launch a ball horizontally, so it's not going off a cliff. Here, you're just throwing it at a Vx of 1.12 meters per second. And we know that the VIY equals 0 because it's horizontal. And the table, actually it is coming off a table, so it's launched off a table. The table is going to be 0.77 meters. Well, that's going to be your Y. And now the question's asking you for X. How far downrange will that ball land when it hits the ground? Right there. So let's plug in our values. You have an X of 1.12 meters per second for Vx. We have a distance down, a Y of 0.77 meters. We are starting horizontally, so VIY is 0. We're accelerating due to gravity, so G is 10 meters per second squared down. And then it asks you for how far, so we're asked for X. And then we're trying to find time. We have enough information to start with the Y-axis, just like before. We have a height. With this information known, we can go to that equation, and we know our G. We plug in our values, and we get 0.39 seconds. So we solve for 0.39 seconds here, but then we can go ahead and populate the x-axis and go to our old faithful equation in the x-axis, x equals v times t, and we can plug in our values. And you're going to get a displacement. So this displacement right here is going to be 0.44 meters. It's not going to be very far. Next problem, ball was kicked horizontally off a cliff. So we've got a cliff. Notice a common theme to these problems. We're going horizontally at 15 meters per second. How high was the cliff? Okay, so how high was the cliff? Y equals question mark. How high is this? If the ball lands 83 meters downrange. So when this happens, it's going to land down here. Once again, have pictures. You're going to help yourself out. You're not going to mix up the givens as much, and you get used to some of the terminology. So we have a Vx of 15 meters per second. It's going to land 83 meters forward. We don't know our y. We want to find that. We know that we're going to start off with a VIY of 0 because it's not going to be falling until the problem starts. We know it's going to be in free fall, so we have our 10 meters per second squared down in the y-axis, and then we're trying to solve for time. Here we have enough information to start with solving for time in the x-axis. So we go ahead and go there, plug in our values, and you're going to get 5.53 seconds. You notice it's falling a distance, so it's a little more than some of the previous problems. And once we have our distance there, we're going to go ahead and plug it into our y-axis, and that's going to end up being 5.53 here. And then we can go to this equation, plugging in 0 for our initial velocity, cancels this first part out, and we plug in all our values, 1/2 times 10 times 5.53 squared, and we get y equals 1.52.9 meters, and that's how high this object is, or how high this cliff was. So here you might have the word tall. So if you're talking about how high the cliff was, we're not talking about how far the ball landed. So we're not talking down. We're actually, the question's asking you how much up were you. So you just have to kind of think of the perspective too of the question in some of your answers. Okay, let's keep on going. Circle your answers just to keep them easy to see, easy for me to grade if I'm grading your work. Josh throws a dart horizontally from a height of his head at 30 meters per second. So here's Josh throwing a dart. It's where you can get a little drawing practice for art class. You're throwing a dart, and it's going to be going at a velocity of 30 meters per second. It's horizontally thrown. It's going to land 18 meters away. So this is going to be your X right here. So 18 meters away. How tall was Josh? So we're trying to find out what is the Y of Josh right here. We have this information. We're going to go ahead and start populating our givens list. He's throwing it from his head. The horizontal velocity is 30 meters per second. He's landing 18 meters away. We're asked for how tall he is. So he's throwing it from his head. So it's going to be whatever the Y is going to be his height. We're going to start just horizontally. So there's your 0 meters per second. It's going to be in free fall. So there's your acceleration due to gravity. Now we're solving for time. And if you take a look, we have enough information to start with our x-axis. So we're going to start with the x-axis here, and we're going to start plugging in our variables, 18 over 30, and we get 0.6 seconds there, and we can populate the y-axis now too, because it's going to have 8.6 seconds to fall. So how far can something go down in 0.6 seconds? That's our new question, and that gets us to this equation. Plug in the 0 for y, that gets rid of this whole first part. Doesn't matter what t is. So you can have 0 times t if you want times 0.6, but it's going to be the same thing. It's probably not a bad idea just to have 0 times 0.6. So when we get to any more difficult problems, when this isn't 0, we might have to do something not to forget about it. And we get 1.8 meters. Once again, like before, it's going to fall 1.8 meters, but here it's asking you how tall was Josh. So that's where the tall could be. If I ask you for a full answer, that would be the best full answer. For the most part, 1.8 meters is going to be fine. Okay, 5. Josh throws the dart horizontally from the height of his head at 30 meters per second. The dart lands 18 meters away. How fast vertically is the dart falling when it hit the ground? So what we're going to do here is this is the same problem as before, and we would have solved for time the same way as before. But what I want you to realize is here it's asking you for something different. And so because it's asking you for VFY, we're going to ignore this x-axis. We used it before to find all the information here. And we can use these givens, and we can find our closest formula where we can solve for the final velocity in the y-axis. And the easiest one to go to is going to be this one right here. So here we have VF, and when we specialize it in the y-axis, the initial velocity in the y-axis, and our g, plug those in, and now we take the data from this table. So VIY is equal to 0, g is the 10, and the time is 6, and we can solve for the velocity that it would hit the ground. And when we say when it hit the ground, we're talking about the moment before it actually stops. It was traveling a velocity of 6 meters per second before it actually stopped. Okay, so let's keep on going. Let's see the next problem. Once again, it's going to be enough information in the x or enough information in the y-axis, and then from there you're going to solve for time and you can go to the next axis. Okay, but baseball rolls off of so in this case you're rolling off of a desk that is a y of 1.20 meters. And it's going to strike the floor at 0.5 meters away, so it's not to scale, but it's going to strike the floor around maybe here, with an x of 0.5 meters. And the question is asking you, what was your Vx? How fast was it rolling? It rolled off the table, so when it rolled off the table, it was only traveling horizontally, so it's asking you for your Vx. So let's go ahead and start populating this. How fast was it rolling? There's our question. There's your Vx equals question. Then throwing in the y-axis height, 1.2 meters down, throwing in the other information we have, the floor, it's going to hit the floor 0.5 meters away, and then it's going to fall from rest in the y-axis. It's going to be in free fall. It's going to accelerate at 10 meters per second squared down, and now we're going to solve for time, and we see that we have enough information to solve for time here. We're going to go to our equation over that equation, which only works if the VIY is 0. We're going to plug in our values. We're going to solve for our time here, and then we're going to go ahead and move that to the x-axis because that's when it's allowed to stop moving forward. And this one I'd go to v equals x over t, but if you want to, in your equation sheet, if this is the equation you have, all you have to do is rearrange it. But it's already rearranged in your 1D motion section of your equation sheet, v equals x over t, and we're just going to plug in our values, and we get 1.02 meters per second. Okay, a pelican's flying horizontally and drops a fish from a height of 8.1 meters. So let's just go and draw out the picture. You have a pelican. If you want to draw a bird, you can draw a bird. There's my pelican. And it's flying horizontally, and it is from a height of 8.1 meters. The fish travels, so the fish is going to land 9.3 meters horizontally from where the pelican was from the base. So that's going to be downrange before it hits the ground. What was the pelican's speed? We're asked for Vx. We're trying to find that right there. So we're going to go to our givens list. We're trying to solve for that. We know this information. It's 8.1 meters high, so it's going to fall down that much. We know that it's going to land 9.3 meters from the base. We know its initial velocity is going to be 0 in the y-axis because it was flying horizontally. We know it's in free fall, so it's going to be 10 meters per second squared as your down as your g, and we're solving for t. We have enough information to solve for t here. We're going to go ahead and go to our t equals square root of 2y over g equation. We plug in our values, and we get 1.27 seconds here. and we're going to move that to the x-axis, and we're going to finish off the formula solving for the x velocity, plugging in our values, and we get 7.32 meters per second. Okay, one more problem. If you launch a ball horizontally moving at a speed of, so you're launching a ball horizontally with a Vx of 2.0 meters per second from a table that's 1.5 meters tall, so y equals 1.5 meters. How far from the base will it land? X equals question mark. So I'm just mixing these up to get you used to picking out your givens and doing all the different parts, but make sure you draw the picture. That will help a lot in doing these problems. We're not going to SOHCAHTOA because this is not a triangle. This is a curved parabolic path. You have to break the x and y axis out separately. It's the only way to do these problems. So filling in your givens, your Vx was 2 meters per second. It falls a y of 1.5 meters down. It starts from rest because it's just starting off of table or off of it's just thrown horizontally, so it's not starting down yet. It's in free fall. It's allowed to fall through the air, so the acceleration due to gravity is going to be that 10 meters per second squared down. And then it asks you for x, and then we have to tie the two together by time, and we have enough information to start for time there. We're going to plug in our values to our 2y over g equation, and we're going to get 0.54 seconds. So it's going to take 0.54 seconds to reach the ground. That's the time we're allowed to stop going forward. We get back to our x equals v times t. We plug in our values, and when you multiply that out, you get 1.1 meters forward. So that's how far from the base. That's how far from the base of the cliff that ball would land right there, 1.1 meters.